Hello, this is my Physics CPT by Abdulrahman Mirsal. Today I will be covering three important and interesting units. And they will be Unit 2, which is Energy and Momentum, Unit 4, Wave Nature of Light, and Unit 5, Matter Energy Interface. For Unit 2, we're going to be covering specific things in it, which is work done by constant force, kinetic energy, and work energy theorem. Second thing is the gravitational potential energy at Earth's surface. The third thing is the law of conservation of energy. And the last thing is elastic potential energy and simple harmonic motion. For energy and work, kinetic energy has a formula of K is equal to half mv squared, which another way of saying it is J is equal to kilograms kg m squared over s squared. For work done by constant force, we have work is equal to force times distance. Another way of saying it, if we have an angle, right as you see here in the photo on the side, it's force times distance cosine theta. The final thing, which is the work of kinetic energy theorem, is delta K is equal to K final minus Ki, which is another way of saying work. Gravitational potential energy. So we need to know what gravitational potential energy is. Okay, so an object at a distance r from a center of Earth, e.g., which is Earth gravitational, is equal to gravity m times negative 1 over y to the power of r. Another way of saying this, where this comes from, this is where the final formula comes from. We multiply that by eg is equal to gm minus 1 over r minus negative 1 over infinity, which gives us the Eg is equal to negative G mm over R. That is the gravitational potential energy formula. Now, we have defined Eg is equal to 0 at infinity, and any finite separation R is below infinity and is therefore negative. As in our uniform gravitational field, the definition near the surface of the Earth, the Eg is smaller, more negative as the separation decreases. Now, the law of the conservation of energy. Energy cannot be created or destroyed, and energy may change from one form to another, but the total amount of energy stays the same. So basically, I could turn electric energy to thermal energy throughout time, but that cannot be destroyed or created. Here's elastic. This is the elastic, as we mentioned in the top, elastic potential energy and simple harmonic motion. These are graphs that are showing the mass of the spring, V as the velocity, and V as the time, and how it works. Our formula for it is negative K is equal to, negative E total minus K is equal to half mv squared, which is negative U is equal to half K x squared. We have time intervals about how the spring works, how you could also see how the position and time relates to velocity and time, and so on. Now to the next unit, Unit 4, which, as we mentioned on the top, wave light. In Unit 4, we will be covering waves in 2 dimensions, diffraction of water waves, interference of waves in 2 dimensions, light, wave, or particle, waves interference, Young's double slit experiment, color and wavelength, polarization of light, differentiation of light through a single slit, diffraction gradient, and interference in thin films, and Michelson interferometer, which is an experiment, and electromagnetic waves and light. Okay, so for waves in 2 dimensions, we need to just know a couple basic things. That many waves have the ability to travel in one or more than one dimension. 2-dimensional waves can have the ability to travel around corners. Sound waves are a good example of 2-dimensional waves, and water waves are also a good visible example of 2-dimensional waves as the result of their water waves. Now, for diffraction of waves impinges on a narrow slit. Here, what happens is the wave goes through one slit, and then you can see how it spreads around in this way. In the first image, top left. The second image, right beside it, wave interference. Both waves, both from 2 different slits, but they do not block each other's wave. Okay, and we could see how the smaller the slit is, the more the wave is spread when it's coming out. Wave impinges on a board slit. When the slit is larger, at a larger scale, the wave itself does not spread as much due to it having space to move in. And the last one, which is barrier, is longer than the wavelength. That is when the wavelength is moving throughout something and the barrier does not allow it to move, it eventually reconnects to each other. But during that space, it stays in its separate ways. It splits and reconnects. Interference of 2-dimensional waves. This alternating pattern of nodes and antinodes continues throughout the construction. Constructive interference occurs when the crest or throws of 2 circle waves meet. Now, as we can see here, This is an example of uh, wave interference with, sorry, this is an example of color and wavelength. So we could see how the wave length differs depending on where it is and how gravity is affecting it. Now we could have dark and destructive interference and bright constructive interference. Basically, dark destructive interference, they go through the same hole, but they do not attract to each other throughout the process. Otherwise, bright constructive interference attracts to it more. We could see that by how they act on angle theta. This is a light beam experiment that shows how waves change throughout polarized light and unpolarized light. As we can see how the movement of the waves before the unpolarized were, and as soon as there was a polarizer and the polarized light came out, the waves started to be one-dimensional. Single slit diffraction. We've mentioned this before. The laser cutting through it, and it just starts spreading, and its light intensity increases on the middle and starts decreasing around, but it still spreads everywhere. We have three types of colors and lights, okay? So, and how they spread. There's visible light through a telescope, visible light, we have visible light and X-ray, right? And all of them are through a telescope. Visible light goes through the telescope and gets hit onto a prism refraction. That makes the two different types of waves go in their separate ways. While visible light going a grating diffraction would make them go in a different dimension. Both, as you can see, the pink waves and the blue waves go up together, and some of them go down together, while there's zero waves in the middle. And same goes for the X-ray light. The indication light is white light. Okay, so this shows how light basically works. Light reflected from both top and bottom surfaces of coating undergoes 180 degrees phase of change. This is equivalent to shifting both waves by half a wavelength. Thickness of the coating is 1/4 of the wavelength of green light in the coating material. Light reflecting from the bottom surface travels an extra distance of half the wavelength of green light. Green light is reflected from the top of the surface, interferes with destructively with green light from the bottom of the surface. In other words, all the green light and the most of the light in the middle of visible spectrum is transmitted. Some red and violet light is reflected, so the coating looks purple. And for the final thing, we could see the electromagnetic spectrum. This is basically what we can see visible in the eye, what's not visible in the eye, and how electromagnetic waves affect that a lot. So there's infrared and ultraviolet, and those what we can't see, and usually the rainbow colors is what we can see. A visible light comes like from a light bulb. Infrared, a good example of it is a TV remote. Ultraviolet is sun. Now, Unit 5, we will be mentioning frame reference and relativity. Relativity of time, length, and momentum, and mass is equal to energy E equals mc squared. Now, for frames and reference and relativity, Einstein's theory began with the study of light and questions about its motion. Since Einstein could not actually observe light, since it moves so fast, he had to think on a way to purely theoretical basis or use a thought experiment. So basically, he could have never discovered for sure, as we can now, how light moves or how waves and particles moves, and he had to only use thought experiment and not exactly visible experiments as he usually should. This is a relativity train robbery. This just shows how velocity, time, and momentum have all together. They all unite. Bullet strikes from A train at 100 millimeter per second, and a bullet from B at 100 minus 50 millimeters per second. Why is that? It's because how the train is moving. So basically, they move the same distance in the same time because the train is moving in the same distance. But if you do the opposite, if you get two trains and you say, oh, one is moving at 100 meters per second and one moves at 150 meters per second, and you shoot both shots in this exact same velocity, you would see the one with 150 meters per second moving slower than the one with 100 meters per second, because that is velocity. If the velocity of the gun, if the shot is 100 meters per second, it's going to be subtracted by the velocity of the train. Now, for the last one, we are going to be talking about relativity and E equals mc squared. This is the special and general relativity. This is a space-time diagram, which is a light cone of how times and space works. And as you can see right here, we are the observer. This is really a theory that has not been all physics is a theory, but this is a way to present relativity equations for momentum, energy, and equations of motion. Last thing is E equals mc squared. This is Albert Einstein's famous discovery, which is energy is equal to mass times speed of light, which is a constant, squared. And yes, that's it. I hope you enjoyed, and thank you for watching.